Hello, class. Mr. Rivers here. I apologize in advance for my voice. I'm a little under the weather and went to the Georgia Tech game yesterday and yelled a little too much, I guess, and lost it. But I think I've got just enough to get through this presentation. So hopefully this is about a 10-minute video. There's going to be 2 practice problems for you to work. I'll tell you what to take notes on and just what to listen to. You're obviously welcome to pause at any time, and I encourage you to do so, and you're welcome to take notes on anything you want to. So let's get going. So the first section we're going to study in term 2 is systems of linear equations. We're going to solve them by graphing. This is section 5.1 in your book. So what is a system of equations? Here I've got 3 examples for you. Take a look at these, see how they're similar, see how they're different. This first one here, you'll see this is 2 equations, both in slope-intercept form. This is a system of equations. The second one here, this is a system of equations as well. 2 equations, both in standard form. And the third here is neither in standard form nor slope-intercept form or point-slope form. So all of these are examples of systems of equations. So a system of equations is a collection of 2 or more equations with a same set of unknowns. I'm going to go and let you finish reading this on your own. So the equations in the system can be linear or nonlinear. We're going to be dealing only with linear equations. You'll get to systems of nonlinear equations as you progress through your mathematical career. So here's a graphical example of a solution to a system of linear equations. Here we've got y equals 4x minus 1. I've graphed that. That is the green line. I've got y equals 2x plus 1. That is the red line. And you'll see they intersect at 1, 3 right there at that point. So our solution is 1, 3. I'm going to talk about this problem for just a moment here. So over here, you'll see my solution is 1, 3. It's the exact same graph you just saw. Watch what happens when I sub in 1 for x and 3 for y into that green equation, y equals 4x minus 1. So we plug in 1 for x, 3 for y. We end up with 3 equals 3, which is true, okay, as you would expect. Same thing over here. We've got y equals 2x plus 1. I've got the point 1, 3. I plug in 1 for x, 3 for y. We end up with 3 equals 3. That is true as well. So we end up with 2 true equations. Let's compare that to this down here. Take a look at the point 0, 1. First, let's find the point 0, 1 on the graph. 0, 1 is that red point right there. Notice the green line does not pass through 0, 1, but the red line does. So 4x minus 1. 4x minus 1 is our green line. Remember, the green line does not pass through 0, 1. So when we plug in 0, 1 for x and y, we end up with 1 equals negative 1, which is false. Meaning, when you get an equation that is false, when you plug in the x and the y values, that means that point is not on the line. As we look at the red equation, 2x plus 1, we plug in 0, 1, and we end up with 1 equals 1, which is true, as you would expect, because 0, 1 is on the red line. Take a look at this one. The point 5, 2. Think about what would happen if you plugged in 5, 2 to the green equation, and what would happen if you plugged in 5, 2 to the red equation. So 5, 2, 1, 2, 3, 4, 5, 1, 2. 5, 2 is over here. 5, 2 is neither on the red line nor is it on the green line. If you were to plug in 5, 2 into the green equation, it would come out to be false. If you were to plug it into the red equation, it would come out to be false. So the point of this is, when you plug in a point to a system of equations, for it to be a solution, it has to make both of the equations true, as we see up here. You cannot make just one of the equations true. This is not the solution. Nor can it make none of the equations true. So it must satisfy both equations in the system of linear equations. That is what's happening algebraically, graphically. Both points both lines will pass through that point. We can classify a few different system of linear equations. There's the situation where we have one solution. We call this a consistent system. We call this consistent because there's at least one solution, the solution being that intersection there. And they are independent equations because the graphs differ from each other. So why do we do this? Well, we just need to identify them one way or another, and this is what the mathematicians who have come before me have decided what these systems will be classified as. So this is consistent due to the solution. It is independent because the line is different. The lines are different from one another. Here we have no solution. These are parallel to each other. We call this inconsistent because there is no solution. These are still independent though because the graphs do differ from one another. Here, this is a line on top of a line. I know you can't tell, but this is a line on top of a line. We have an infinite number of solutions here. This is consistent because we have at least one solution, and these are dependent equations. They are considered dependent when the graphs of the equations are identical. So we'll come across these three different scenarios as we move through this section today and tomorrow. So here's a practice problem. I would like you to graph and find the solution to the following system of equations. Classify the system of linear equations. And when I say classify it, I mean classify it as one of these three: consistent and independent, inconsistent and independent, consistent and dependent. One of those three scenarios. So go ahead and pause the video, graph and find the solution. I would like you to do so on graph paper and show your work algebraically. Pause the video now. Okay, for this particular problem, I've already done the work algebraically. You'll see that here. So for 2x minus y equals 6, remember I can plug in whatever I want to for x. I plugged in x equals 0. You can see my work here. I end up with y equals negative 6. So I got the point 0, negative 6. Let me go ahead and plot that now. So 0, negative 1, 2, 3, 4, 5, 6. That's that point right there. I did the same thing for x equals 4. Why did I pick x equals 4? You can pick whatever you want to. I just picked x equals 4. So plugged in x equals 4, isolate y, and I get y equals 2. So we get the point 4, 2. 1, 2, 3, 4, 1, 2. That's that point right there. For my second equation, I plugged in x equals 0, y. I just seemed like a pretty easy number to plug in, so I did. You get y equals 10 thirds, so you get the point 0 and 10 thirds. 10 thirds is 3 and 1/3, so 0, 1, 2, 3, and 1/3. That's about right there, roughly. And then when I plugged in x equals 4, why did I pick x equals 4? I just had to pick something. So plugged in x equals 4. You can see my work here. Isolate y, and I get 4, 2. 4, 2, 1, 2, 3, 4, 2. It's the same point. So both the top equation and the bottom equation, they both pass through the point 4, 2. So now we'll connect our points with a line. It looks something like this. Oh, that's a bad one. Let me do a better job. I can do better. Let's try that one more time. There we go. That's better. And do the same thing with the other 2 points. There we go. So that's not the prettiest, and you probably did a much better job using graph paper, but you can see when we plot this, they have a solution at 4, 2. So back over here, we have a solution at 4, 2. And now we need to classify this. So which one of these does our graph look like? Looks like that one right there. So when we classify this, we're going to say it's consistent and independent. Consistent and independent. There you go. Okay. Try one more practice problem. Right there. So one more time, show your work algebraically. Pause the video now and graph, find the solutions. Let's go and do that now. All right. Now, you didn't have to do this, but I'm going to isolate y in these two equations. When I isolate y in that top equation, I end up with y equals 1/3 x plus 2. Y equals 1/3 x plus 2 is what you get with that top equation when you isolate y. Okay. I'm going to do the same thing with the bottom equation. Isolate y, let's see what happens. With that bottom equation, you get y equals 1/3 x plus 1. So you can check my work there as well. So when I isolate y, now these two equations kind of take on a new, maybe a new perspective to you. What do you notice about these two equations? And you may have already noticed when you graph them. I notice they have the same slope. Okay, when they have the same slope, they're either going to be parallel or they're going to be on top of one another. So as I analyze the y-intercept, I notice I have different y-intercepts. That lets me know they are not going to intersect. They are going to be parallel to one another. So when you graph these, it should have looked like this. And you notice they are in fact parallel to one another. So as we go to classify these, remember these are the different classifications. The situation where they are parallel to one another, these are inconsistent because there is no solution. They are inconsistent, and they are independent equations because they differ from one another. So inconsistent and independent is what you should have said here. Okay, let me write that. So that was inconsistent and independent. Again, inconsistent because they do not have a solution, and independent because they differ from one another. So you could say there is no solution here. No solution. So just to recap this video, here's what you should know and understand. You should recognize a system of linear equations both algebraically and graphically. So graphically, it's going to look like one of these three scenarios, either two lines which intersect once and only once. There's one solution here. Two lines that do not intersect at all, they are parallel, or two lines that intersect and have an infinite number of solutions. They're on top of one another, so a line on top of a line. That's what they look like graphically. Algebraically, it's going to look something like this. You've got the brace to show you that these are a set of equations that are connected to one another, and then they are two separate equations. You need to be able to graph a system of linear equations. You just did that twice. We're going to do that in class tomorrow. And finally, you should be able to find the solution of the system of linear equations. You should do this graphically by finding the intersection of the two lines. We did that here. So we have an intersection of these two lines. We did that here, the intersection of the two lines. That is the solution to the system of linear equations. And then finally, you should be able to identify that the point that satisfies both equations, meaning it has to make both equations true, that is the solution. And it is an ordered pair because remember, it's a point on the graph. So the point that satisfies both equations is the solution, and that was talked about here. When I plug in my solution, which was 1, 3 in this situation, it made both equations true. If you plug in a point that makes one equation true and the other false, that is not a solution. And of course, if it makes both equations true, like 5, 2, which is not on either of the equations or on either of the lines, then that is not a solution either. So the solution must satisfy both equations, make both of them true. All right, thank you very much, and we'll see you in class tomorrow.